and right now he is with Calcutta University in the pure math department as an assistant professor. His specialties are differential geometry of contact and complex manifolds. And he has published more than 50 papers in international journals and national journals. And I'm very happy that with this young age, he has a lot of publication and very active researcher. And so I welcome him for this talk, and I thank him for accepting to give this talk in this conference on behalf of the IMS organizers and VIT organizers. Without further ado, I invite Dr. Pradip Majhi to continue to start his talk on cotton solitons within the framework of almost Kenmotsu 3H manifolds. Dr. Pradeep, it is yours now.
Okay, thank you, sir.
About just 5 minutes early to the ending, I'll wave my hand so that you can make your conclusions accordingly.
Okay, sir. Okay, thank you very much for the introduction. Let me thank the Indian Mathematical Society, the Executive Council, and the organizing committee of this 86th International Conference of IMS. So today the title of my talk is Cotton Solitons within the framework of almost Kenmotsu 3H manifolds. So before entering in the main topic, cotton soliton, let me first introduce the definition of Ricci solitons. So over the last few years, the Ricci and other geometric flows have been an interesting topic of applied research in both physics and mathematics. So the notion of Ricci soliton was introduced by R.S. Hamilton in 1982. So what is Ricci soliton? Ricci soliton is a triple GV lambda on a Riemannian manifold MG, where G is the Riemannian metric, V is a vector field called potential vector field, and lambda is a constant. It's satisfying the following equations. That is equation 1. So if lambda, the Ricci soliton is said to be sinking, expanding, and steady according as lambda negative, positive, or 0. So in particular, if we consider the potential vector field V is a Killing vector field, then this term, that is lead derivative of G with respect to V, so this term will vanish. So in this case, equation 1 reduces to S minus lambda G, that is G is the Einstein metric. Okay, so we can say that Ricci soliton is the natural generalization of Einstein metric. Natural generalization of the Einstein metric. So also a Ricci soliton can be considered as a fixed point of the Hamiltonian flow. This is the equation of the Hamiltonian flow viewed as a dynamical system. So if the vector field, that is potential vector field, is the gradient of some smooth function minus f, then the equation of the Ricci soliton takes the form this, that is Hesse plus equals to S plus lambda G, where Hesse is the Hessian of the smooth function f, and it is defined by Hesse equals to del 2f, and in this case the metric G is called gradient Ricci soliton. So now we define Yamabe soliton. In order to find matrices of constant curvature in a given conformal class of Riemannian matrices, Hamilton's in 1986 introduced Yamabe flow and gave similar solution to Yamabe flow called Yamabe soliton, and which is a Riemannian metric G satisfying the equation 3. So in this case, R is small r is the scalar curvature with respect to the metric G. So and what is the scalar curvature? Scalar curvature is the trace of the Ricci operator Q. So we'll define Ricci operator later explicitly. Now, inspired by the Hamiltonian's work on Ricci flow, in 2008, Kisisel et al., based on the conformally invariant cotton tensor, introduced a new flow called cotton flow, and this is the differential equation of the cotton flow. where C is the 0 to type cotton tensor of the Riemannian manifold Mg, and from the cotton flow they define the notion of cotton soliton as follows. So a cotton soliton is a metric G defined on a three-dimensional space Mg, satisfying the following equations. That is equation 3. In this case, C is the 0 to type cotton tensor and sigma is a constant. Okay, and V is the potential vector field. So in this case, we have a relation, that is relation between 0 to type cotton tensor and 0 3 type cotton tensor. So here G is the determinant of the metric Gij, and Cij is the 0 3 type cotton tensor, and epsilon is the tensor density. Basically, this is a relation between 0 2 type cotton tensor and this is a 0 3 type cotton tensor. So now, just as the Ricci-Shoridan and Ivy-Shoridan are the fixed point of the Ricci flow and Ivy flow that already we have defined. So therefore, cotton Shoridan are the fixed points of the cotton flow up to diffeomorphism and scaling. Since the Ricci flow is a second order differential equation and the cotton flow is a third order differential equation, so there is a substantial difference between Ricci flow and cotton flow. Even so, cotton solitons are the closely related to the Ricci and Ivy solitons. So using the terminology of Ricci solitons, we call the cotton soliton sinking, steady, and expanding according as sigma positive, 0, and negative, respectively. So cotton soliton is said to be trivial if C equals to 0. That is, cotton tensor equals to 0. So we define cotton tensor later. Now, in particular, if the potential vector field V is a gradient field for some smooth function, say f, then the equation of the cotton soliton takes the form this. So in this case, G is said to be gradient cotton soliton. So for a Riemannian case, so now we'll discuss some results related to the cotton soliton on Riemannian manifold and semi-Riemannian manifold. So in a Riemannian manifold, Lorenzo et al. Proved that a compact Riemannian cotton soliton is locally conformably flat, and in the non-compact case, the existence of non-trivial sinking cotton solitons on a Heisenberg group, they defined it. Okay, and see, again in Lorenzo et al. Proved in a non-Riemannian case that they gave the existence of Lorentzian cotton solitons. Furthermore, Calvirano et al. Studied left invariant cotton solitons on a homogeneous manifolds. So far we have, as far we know, the cotton solitons studied only on Riemannian manifold and semi-Riemannian manifolds. But our aim is to study it in contact metric manifolds. So in the framework of contact geometry, we have noticed that many authors have studied Ricci solitons and Ivy solitons on contact metric manifolds and almost co-Kähler manifolds. For instance, Ricci solitons on contact metric manifold studied by Cho and Sharma, and they consider the potential vector field V is a collinear with Xi. So the potential vector field V is collinear with Xi means V goes to some f Xi where f is a smooth function. And Yamavi solitons on contact metric manifold studied by Venkatesh and Nair. So in this case, they considered the assumption Q phi equals to phi Q. That is, phi is the 1-1 Ricci tensor, Q is the 1-1 Ricci operator. And they proved that in this case, the manifold is flat and it has a constant scalar curvature. Recently, Yamavi solitons on almost co-Kähler manifold as well as on Kemi almost co-Kähler manifold studied by Shu, Professor Shu, Korean mathematician. And in Wang recently studied almost co-Kähler manifolds with a Ricci soliton whose potential vector field is non-zero pointers collinear with the Rip vector field, as well as gradient Ricci solitons on Kemi almost co-Kähler manifolds. So as far we know that cotton solitons were studied by X chain on certain almost contact metric manifold, speciously on almost co-Kähler 3 manifolds. So motivated by the studies of X chain, we consider the notion of cotton soliton on an almost K-meso 3H manifolds and prove some related results. So in we proved these two results. So mainly these two results. So to prove this result, we need to prove some lemmas and propositions. So we'll discuss the proof of these theorems later. So let me develop some notations also. So almost K-mesh manifolds. So and almost contact metric manifold is an odd dimensional smooth manifolds together with the structure phi j eta g, where phi is a one-on tensor field, j is a unit vector called a Reeve vector field, and eta is a one form and is defined by eta x equals to gxy, and g is a Riemannian metric defined by the equation 8. So in this case, from the equation 7, it can be easily derived that phi j equals to 0 and eta phi equals to 0. So the fundamental true form, we define the fundamental true form capital phi on an almost contact manifold, metric manifold, defined by capital phi xy equals to gx phi y for all any smooth vector fields xy on Mn. So now we define the normality of an almost contact metric manifold. So the conditions for an almost contact metric manifold being normal is equivalent to vanishing of the 1-2 type torsion tensor n phi, defined by n phi equals to this. So this bracket phi is the Nijen-Huis tensor of phi, and almost contact metric manifold such that eta is closed. Eta is closed means the exterior differentiation of eta is 0, and d phi means this phi. That is fundamental true point. So d phi equals to 2 eta wedge product capital phi. So an almost contact metric manifold with this condition, that is eta is closed and d phi equals to 2 eta wedge phi, are called almost Kenmetsu manifolds. So a normal almost Kenmetsu manifolds is a Kenmetsu manifolds. We have already defined what is normal contact metric manifold. So also a Kenmetsu manifold can be characterized by this equation for any smooth vector fields xy on Mn. Mn mean M2n plus 1, that is contact metric manifold of dimension 2n plus 1. So now we define some tensors, that is L, H, and H prime on a three-dimensional almost Kenmetsu manifolds. So we define L equals to R dot xi. That is the first component is dot means x varies freely. That is Lx equals to Rx xi. Okay. So H equals to half Lie derivative of phi with respect to xi, and H prime equals to H composition phi. So it is known that the operator L and H are the symmetric operators, and the operators L and H are satisfy the following relations 9, 10, and 11. So here nabla is the Levi-Civita connection or the Riemannian connection. So now we defined almost Kenmetsu 3H manifolds because our target is to find target is to study cotton solitons on almost Kenmetsu 3H manifolds. So what is almost Kenmetsu 3H manifolds? So a three-dimensional almost Kenmetsu manifold is called an almost Kenmetsu 3H manifolds if it satisfies nabla xi h equals to 0. Okay, so now we define cotton tensor. So the 0-3 type cotton tensor of a three-dimensional Riemannian manifold is defined by this equation, that is equation 12. So here S is the 0-2 type Ricci tensor, and small r is the scalar curvature that already we have mentioned. And it is known that the cotton tensor is skew symmetric with respect to these first two indices, that is x, y, and it is totally trace free. So it is known that for n greater equals to 4, that is dimension strictly greater than 3, and n-dimensional Riemannian manifold is conformally flat if the Weil conformal curvature tensor vanish. So this is Weil conformal curvature tensor or Weil tensor. So they are the same synonym. So Weil tensor vanish. So for n equals to 3, it is known that Weil tensor always vanishes. So but the cotton tensor does not vanish in general. So in n equals to 3, the cotton tensor play the role of Weil tensor. So now we'll sketch the proof of our theorem that we have already mentioned. So for that, we need to develop some notations and results. So let U1 be the maximal open subset of a three-dimensional almost Kenmetsu manifolds M3 such that H equals to 0, and U2 be the maximal open subset on which H equals to 0. Then U1 union U2 is an open dense subset of M3. So in U, then U1 is a non-empty, and in U1 there is a local orthonormal basis, that is Xi E phi, and such that H equals to lambda E and H phi equals to minus lambda phi. That is eigenvalue of H is lambda corresponding to the eigenvector E, and eigenvalue of H is minus lambda corresponding to the eigenvector phi. So for some positive function lambda, so since we are considering almost Kenmesu 3H manifolds, so in our case nabla Xi H equals to 0, and if we use the lemma 6 of the Cho's paper, J.T. Cho's paper, a Korean mathematician, then we can calculate. This is a very big computation. So we can calculate the coefficient of the Riemannian connection nabla of an almost Kenmesu 3H manifold with respect to a local orthonormal basis Xi phi. So these are all the coefficient of the Riemannian connection nabla. There are 9 coefficient of the Riemannian connection nabla. This is Riemannian connection or Levi-Civita connection. So from this coefficient of the Riemannian connection, we can easily calculate the Lie brackets. So these are all Lie brackets. So 3 Lie brackets are there. So there is a relation between Lie bracket and Levi-Civita connection or Riemannian connection. That is Lie bracket xy equals to nabla xy minus nabla yx for all xy for all smooth vector field xy. So you can easily calculate from the coefficient of Riemannian connection nabla the Lie bracket terms. Okay. So now we'll again find the coefficient of the Ricci operator Q. So if we find the coefficient of the Ricci operator Q, and these are the all coefficients, this is again a calculation. I am omitting that part. So on U1, the Ricci operator of an almost Kenmesu 3H manifold with respect to a local orthonormal basis Xi E phi is given by this. So these are all coefficient of the 1-1 type Ricci operator Q. And it is known that the scalar curvature R is the trace of the Ricci operator Q. Okay. So since we have the expression of Ricci operator, so we can easily calculate the scalar curvature here. So the scalar curvatures are -2 into lambda square plus 1 minus 2f. So we'll use it later. So using lemma 5, we can obtain the 0 to type Ricci tensor also. I mean 0 to type Ricci tensor. So there is a relation between 0 to type Ricci tensor and Ricci operator 1-1 Ricci operator. And what is the relation? That is xy equals to gqxy for any xy smooth vector field. So it is known that an almost Kenmesu 3 manifold is Kenmesu if and only if h equals to 0. So in our case, if h equals to 0, then nabla Xi h equals always 0. So thus a Kenmesu metric always admits a almost Kenmesu 3H structure. So now an example. So we are considering non-Kenmesu almost Kenmesu structure. Here is an example. That is example 6 of non-Kenmesu almost Kenmesu 3H manifold. So this is an example of non-Kenmesu almost Kenmesu 3H manifold. So we use this example later in our main theorem. So now our aim is to we like to study the cotton solitons in non-Kenmesu almost Kenmesu 3H manifolds. So in this regard, we prove the following lemmas. So this is the lemma. So in the orthonormal plane field Xi phi, we have this this lemma says in an orthonormal plane field Xi phi, the components of 0-2 type cotton tensor, okay, on of an non-Kenmesu almost Kenmesu 3H manifold is this. There are the six components are there. These are all independent components. 6 components are there. So we can calculate these 6 components. So the idea is for with respect to an orthonormal frame field Xi E phi of a non-Kenmesu almost Kenmesu 3H M3 manifold. the components of the metric tensor G is the identity matrix. Okay, so in this case, G is equals to determinant of Gij, that is small g equals to determinant of Gij, and that is equals to 1. So just remember the equation 5 reduces to this, that is the relation between 0,2 type cotton tensor and 0,3 type cotton tensor. So if we use the value of G here, we'll get this, right? So now we have these 6 components. C11, C12 up to C33, these 6 components. Now, if you have, now we'll use the definition of cotton tensor, 0,3 type cotton tensor that already we have defined in equation 12. So making use of equation 12, we'll get the coefficient of cotton tensor 0,2 type cotton tensor is this, right? C11 up to C33. That is from the equation 23 to 28. Now, to find the explicit expression of the 0,2 type cotton tensor, we need to calculate the derivative of 0,2 type Ricci tensor. So for that, we have to calculate this. Now, after calculating, we have these 6 pair of equations from 29 to 34. These 6 pair of equations. So if we back substitute this 6 pair of equations, that is from 29 to 34, we'll get back substitute here 23 to 28, we'll get the explicit expression of cotton tensor, 0,2 type cotton tensor, that is in lemma 7. So this is just a sketch of the proof of this lemma. Now we'll prove a proposition. So this proposition says that if we consider the Reed vector field Chi is an eigenvector of the Ricci operator Q, then the non-Kenmeshu almost Kenmeshu 3H manifolds is locally isometric to a non-unimodular Lie group equipped with a left invariant non-Kenmeshu almost Kenmeshu structure. So in this case, since Chi is an eigenvalue of the Ricci operator Q, so we have from the lemma 5. So please remember lemma 5. We have in lemma 5 the expression of the one-on type Ricci tensor. So we will use this part here. So we'll get equation 35. Okay. So now it is known that the divergence of Q, that is divergence of the Ricci operator Q, is half drx or xr. That is, I mean, x is a vector field operating on its function. That is ultimately xr is a function, scalar valued function. Okay. So now if we use this value here explicitly after some calculations, I'm opening this part, we'll get this part of the Lie bracket, these 3 Lie brackets part. So now we compare this part of Lie bracket with Milner's result already we have defined in example 6. Okay, we'll get our results, that is M3 is a locally isometric to the unimodular Lie group equipped with a left invariant non-Kenmeshu almost Kenmeshu structure. Now we'll use this proposition with lemma 7. So if we combine the proposition 0.1 with lemma 7, we have the coefficient of cotton tensor is this. Okay, so there are 6 coefficient of cotton tensor. So the extra condition is in this case the Reed vector field is an eigenvector of the Ricci operator Q. That's why we have this shorter form of 0,2 type cotton tensor in corollary 8. Now we first prove the cotton soliton. In this case, we are considered the potential vector field V is pointwise collinear with the Reed vector field. So in this regards, we prove the following non-existing result. So on a non-Kenmeshu almost Kenmeshu 3H manifold, such that the Reed vector field is an eigenvector of the Ricci operator, there exists no cotton soliton with potential vector field pointwise collinear with the Reed vector field. So we'll prove this part. So this proof on very simple proof. So we just use lemma 4 and corollary 8. Okay, and we'll use this part. We'll use the contradiction method here. So from the theorem 9 and lemma 0.1, if we combine this one, we'll get the corollary 10. That is, on a three-dimensional non-unimodular Lie group equipped with the left invariant non-convex to almost convex structure, there exists cotton soliton with potential vector field pointwise collinear with the Rip vector field. So next we consider the potential vector field V as orthogonal to the Rip vector field. That is, V is orthogonal to Xi. So in this case, in this setting, we prove the following. So let M3 be a non-convex to almost convex to 3H manifold such that the Rip vector field is an eigenvector of the Ricci operator. If G is a cotton soliton with potential vector field orthogonal to the Rip vector field, then M3 is a locally isometric to the product manifold. This is hyperbolic space, and this is R, that is product manifold. And in this case, the cotton soliton is steady. So the idea of the proof is, for since we are considering V is orthogonal to Xi, since we are considered V orthogonal to Xi, then V can be written as in this way, that is V equals to alpha 1 E plus alpha 2 phi E, right? So alpha 1, alpha 2 are some smooth functions. So with the help of lemma 4, so in the lemma 4, we have the expressions of the Riemannian connection, right? Nabla. So with the help of the lemma 4, we can easily calculate the Lie derivative part of G with respect to V here. So here there are six components are there for this Lie derivative part. So if we use this first component, in the definition of cotton soliton, that is equation 4, we'll get sigma equals to 0. Okay, and sigma equals to 0 means the cotton soliton is steady, right? Sigma equals to 0 means the cotton soliton is steady. So now if we use the rest equation of 42, we'll have this equation, and after some calculation, we are omitting this calculating part here because this is very long technical calculation. So we'll get ultimately lambda equals to 1. We'll get ultimately lambda equals to 1. So if we use lambda equals to 1, we'll get nabla q equals to 0. Nabla q equals to 0 means the Ricci tensor is parallel. See, lambda is a Levi-Ceuta connection. And it is known that in a Riemannian, three-dimensional Riemannian manifold, Ricci parallel is necessary. I mean, a manifold is Ricci parallel if and only if it is locally symmetric. And it is known that by Professor Cho's result, that is Korean mathematician, Cho's result that a non-convex to almost convex to 3 manifold, M3 is locally locally symmetric if and only if it is locally isometric to this product space. So now by using these results of Cho, we'll get our main results. Our main results means that is this result. Okay. That is, if G is a cotton with a potential vector field orthogonal to the Rip vector field, then M3 is a locally isometric to the this product space, and the cotton is steady. Okay. Again, I am saying this is very technical and big calculation. I am just giving you the sketch of this proof. Okay, sketch of the proof. Now, if we combine the proposition 1, 0.1 and theorem 11, we will get a corollary. And the corollary says, if G is a cotton with potential vector field orthogonal to the Rip vector field on a three-dimensional non-modular Lie group M3 equipped with a left invariant non-convex to almost convex structure, then M3 is a locally isometric to the product space this, and the cotton in this case steady. So this is all about our results, and these papers already in the archive. If anyone can interest, you can see the archive. And this is a communicated paper, and we communicate this in our channel of mathematical sciences. And this is a joint work with my student Dibakar. Okay, so I am suggesting a few problems. So in my opinion, one can study some problems in this area if anybody interested in this area. So gradient cotton soliton on almost NMS through 3H manifold, and cotton soliton and gradient cotton soliton on KMU almost co-Euler manifolds. So I'm suggesting this problem. I don't know whether this problem is valid or not. So if anybody can interested, then you can try. So these are my references that already have mentioned. These are the references I used here. These are the references I used here. Finally, thank you very much for your attention.
Thank you. Any questions from the audience? Any questions or comments? Okay, so if there are no questions, I thank Dr. Pradip Majhi for giving an informative talk on this manifold structures and Ricky flows and generalizing all those things. I thank you very much. I thank the organizers for giving me this opportunity. Thank you, one and all. Thank you.
Thank you very much, sir. I like to thank also the Indian Mathematical Society, especially Professor Sotyadev sir and Professor Pijis Chandra sir, and the PIT Vellore, the local organizing committee, for this nice international conference. Thank you for your kind attention.
Thank you, Professor Dr. Yuvraj sir. Nicely handled the sessions, and you have given valuable time to us. Thank you, Professor Dr. Majhi. You have given very nice talk, presented very nicely. Thank you very much, sir.
Thank you,
sir. Thank you.
Thank you.
Thank you.